Welcome to Microlecture 2 on formal charges and bond polarity. I've got a better periodic table now. This one has more than just carbon on it. I want to remind you that the valence count for any of these elements is going to be the group number. So carbon is 4, oxygen is 6. And I'm reminding you of this because we're going to be using the valence count in our formal charge calculation. So we can calculate the formal charge on an atom by taking the number of valence electrons, so the group number, and subtracting off 1/2 the number of electrons in a covalent bond that is attached to that atom, and then subtract off the number of electrons involved in lone pairs that are on that atom. A more simplified way of thinking about it is formal charge is group number minus the number of covalent bonds minus the number of electrons in lone pairs. A quick example here with methane, CH4. So the number of bonding electrons is 2 for the hydrogens and 8 for the carbon. Remember, we're going to subtract off half of that number, or we could just say the number of covalent bonds instead. So the formal charge calculation for hydrogen becomes 1, the valence count, minus 1, the number of covalent bonds, minus 0, the number of electrons that are lone pair electrons. Likewise, the formal charge calculation for carbon is the group number 4 minus 4 covalent bonds and minus 0 lone pair electrons. So the formal charge equals 0 on both of these atoms. In the event that we have a non-zero formal charge, we must label that atom with its formal charge. So let's do an example of formal charge calculation. You'll remember this compound from our last microlecture. Let's go back and draw those valid Lewis structures, but this time include the necessary formal charge. So if you recall, these were the two valid Lewis structures for diazomethane. Let's go ahead and calculate formal charge for the atoms involved. So we could do the hydrogen atom here. It has a valence of 1. It has 1 covalent bond and 0 lone pairs. So it has a formal charge of 0. And usually if there's a formal charge of 0, we don't do anything to indicate so on the structure. Let's go with this carbon here next. This carbon has a valence of 4. There are 4 covalent bonds attached to this carbon and no lone pairs. So that equals a formal charge of 0. And the nitrogen here. This nitrogen has a valence of 5. It has 4 covalent bonds and it has 0 lone pairs. So that is a formal charge of 1. And so I would want to indicate that by circling a positive charge. So a +1 formal charge on the nitrogen. We don't use just positive because the lines can get confusing in skeletal structures and look like bonds. So we circle formal charges always. Lastly, this nitrogen over here, it has a valence of 5, it has 2 covalent bonds, and it has a total of 4 valence electrons. So that equals a -1 formal charge, and so I would circle the minus sign. It's very rare to have formal charges greater than 1. And that means plus or minus, so 1 plus or 1 minus. It happens that we have 2 plus or 2 minus charges occasionally, very rarely, but it's highly unlikely. In the next structure, then we've already solved for the hydrogen that has one bond. It's bonded exactly the same way, so that has a formal charge of 0. The carbon here, carbon has a valence of 4. There are 3 covalent bonds here and 2 non-bonding electrons. So this carbon has a formal charge of minus. We would circle the minus charge and put it near the carbon. Nitrogen with 4 bonds and no lone pairs, valence of 5, has a +1 formal charge. So I put a plus right there. And then this last nitrogen, valence of 5, 3 covalent bonds, and 2 lone pair electrons. So no formal charge. You see, either way, it's a net neutral compound. There's a negative charge right next to a positive charge in both structures. I'd like to remind you of the concept of electronegativity. This is a periodic trend that increases as you move up and to the right of the periodic table. So fluorine is the most electronegative element according to the Pauling scale of electronegativity. As a reminder, electronegativity is a desire to be surrounded by electrons in the form of bonds. When an atom with high electronegativity bonds covalently to an atom with low electronegativity or lower electronegativity, the result is a polar covalent bond. When there are small electronegativity differences between the atoms in a covalent bond, that bond is said to be non-polar. So when we're drawing an organic compound and there is a polar covalent bond involved, we can indicate that with a crosshair and arrow or a delta plus delta minus notation. When using the crosshair and arrow, point the arrowhead toward the more electronegative atom, and the crosshair goes on the more electropositive atom. Alternatively, you can use the delta plus and delta minus notation. Delta minus is often used to label a more electronegative atom in a polar covalent bond. And so the last idea here is that we can actually quantify bond polarity. Another name for bond polarity is dipole moment, and dipole moments have units of debye. There are 2 factors that go into the calculation for dipole moment, and they are the bond length and the difference in electronegativity between the 2 atoms. This explains why a carbon-fluorine bond has a greater difference in electronegativity than a carbon-oxygen double bond, but it's actually much less polar.